Okay, so this is the first time we record this kind of video. Hopefully, the quality is fine. So we in last class we talked about the control system. Basically, we discussed about the at the very beginning we talk about the open loop control. Then later on we talk about the closed loop control, right? So for the open loop control, and what we do is we have a transfer function, and this u s is the input, and y s is the output, and ps is our actually the transfer function. So this is, as we know, transfer function actually describes the whole system, dynamics of the whole system. So and if we put instead of putting the equation there, then we put this kind of blocks. And this is something called a block diagram, and this is something you'll probably see is pretty new. Then what we try to do here is that instead of just put this in the block diagram, we try to do some kind of control on it. And you might realize that the difference here is the block diagram, regular block diagram, this input is US as what we get used to see. And then now we change this block diagram a little bit. And if you see here, the input is no longer our input to the system, US. Here, instead, we put the desired value, which is the value whatever you want to reach. And this we call UD. Is called desired output signal. And then we put a control block here. The input to the system actually is after the input signal passing through this block diagram. Let me see whether I can use the pen here to give you some idea. So essentially, this is the input here. This is actually our input US. So the US is no longer at the very beginning of the block diagram, but it after pass through the controller, or then this will be our input. Okay, so this is the difference between previous, what we get used to see is we have the input at the very beginning, then output is the outside. But now we put this at the very beginning of the signal. We wanted to see what kind of signal we want to get, and this as the input for our system design. The key thing here, we try to design the controller so that the system could be stable, or could be could be reach the level we want, or anything we want to get. So for example, if we want to get a displacement to a certain kind of level, let's say this is our input. The actual output, of course, we want to eventually get the actual output to be the same as our desired value. But a lot of times the actual output of ys is not actually the desired value. So that's why we try to design some kind of controller so that we can do that. And the block diagram here, if you can see here, we have very straightforward YDS times CS is our actual input signal, US. Then if we have some kind of disturbance get into the system, now we will be able to get this, get the PS before we put it into the system, either has the US plus the disturbance to our dynamic system. And these two things combined will be getting into our output. Okay, so then if you put all this kind of system together, then we can actually write the transfer function, right? So we have this ys equal us times times ps. If we ignore this ds, assume there are no disturbance. And what we want is our actually us equal our ds, yds, ys equal our yds. And from here you can see that the controller actually is just the inverse of this transfer function, or inverse of a ps. And this gives us insight that if we want to actually precisely get the signal we want, okay, precisely get the signal we want, and if we precisely know this kind of transfer function or the dynamics of the system through the modeling, then we will be able to actually get the system, get this kind of signal we want by put the controller as the inverse of this inverse of the system. And on top of that, as you can see here from this duration, we ignore this disturbance, meaning that there is no disturbance at all. As you can imagine, this kind of system, will work if everything is under precise control and precise analyzed. Then this can work pretty well. And we discussed that, this something called open loop control. There's no feedback, nothing, and just straightforward. And we can do it if we precisely know that. But in reality, this is something very difficult, right? So you probably can still remember that when I talk about, when you're working on these stairs, if you work so many times, you know how to work even without looking at these stairs. But in reality, and if something changes, and this could be a problem, right? So if that's what we try to see whether we can design system by getting some feedback, or just like when you're working on stairs, you use your eye to get feedback, and from there whether we can do something better. So the idea is very simple. Assume here there are no disturbance again, because to try to simplify the analysis later on, we'll talk about if the system has disturbance, whether we can handle this kind of scenario. So if there is no disturbance, and we try to design controller, but at the same time we try to get a signal output. Okay, if we have ys at that time, now we get a signal output and combine with our desired signal. So this combination actually try to take the difference or the error, how much it's away from our desired signal. So the controller essentially is, we try to the input of controller is the difference of this desired signal and this real output signal. The real output signal typically use sensor, like for human, when you work, you use eye as the feedback, right? For those people who cannot see, they use other sense to get this feedback, or some kind of vision system to send it to the controller and get to the difference between the desired signal. Then we try to design controller from there. So let's give you, for the example we presented last class, is that we have DC motor, and we know how we can model this kind of DC motor and assume that DC motor has no inductance, which we prove that this inference of this kind of DC motor is very, very small. Then we say this system has no loading either, and this, of course, as I mentioned, this kind of, if we design a motor and without any loading, and it seems like it does not make sense. But in reality, when you design any motor, you want to test this kind of motor before you do any loading. So you want to make sure this motor perform properly, and then you can put some loading there. This is just do the testing step by step. Now we start from here. Let's say we want to control this the position, or we try to get the position signal what we want. So from our previous modeling, we know that the v here is the velocity. So here the velocity v. I want to put it here. So this is the velocity. Okay, this is the velocity of the signal, and if we want to do the position, we know the velocity is the position derivative position, right? Then in the s domain, it will be s times sx xs. So if we put it into this equation, we can get this transfer function, which is xs divided by ei. And as you can see here, as we discussed last class, the system is not stable because we have a pole that is 0. So this is unstable system, and then we can see whether we can convert this kind of unstable system to stable system through this kind of control system design. That's our goal, and we try to simplify this kind of modeling by I just put a different variable, the C1, C2, or everything here, right? So then what we say, the easiest controller is just like we put a linear sense here. CS just a constant. Okay, that's very straightforward, right? If we do not want to do anything fancy, we just say the signal coming to the controller, we just put a scaling factor there to see whether this kind of system actually will work. What we find out from last class is that actually this is, if this CS is constant, first of all, the system is stable. Okay, if the K is larger than 0, the system is stable. That's great, right? So that's what the first goal is reached. We basically say, if the system, if we have this K is is a positive number, then the system is always stable. And on top of that, the steady state response of the signal is always our desired signal. That's also good news, right? So we want our signal to be the same as our input, the output signal to be what we desired. And if the system stabilizes at that level, then that'll be great. So that's two things we, first of all, we make this unstable system to be stable. And a second goal we reached from this example is that we actually can make our make our system steady state response always to be the desired value, just through the very simple controller like the linear scaling controller. Okay, so that's what we discussed in last class, and we'll see whether we can do more analysis to see whether this kind of controller is ideal, or whether this kind of controller is what we want. Okay, so if we put this kind of system into block diagram, if you look at this block diagram here, so you have this GS here, you can put it into GS here. Again, this closed loop transfer function, I have XD here instead of US. I have the desired signal, the output is our real signal. This is called a closed loop control system, right? So from here, we try to do more analysis and to see whether we get some property of signal of system actually meet our needs, right? So that's what we try to do. So let me stop this video, and I record the second part of this video. Hopefully we combine the video, make everything easier. Okay, so let's see. I try to stop.